In today's lecture, we will discuss reciprocal system of vectors. To begin with, let us consider three known coplanar vectors A, B, and C. So these are non-coplanar vectors. Now if they are non-coplanar, this would mean that the scalar product, the scalar triple product of the three vectors is going to be not equals to 0. It cannot be equals to 0 if the three vectors are non-coplanar. Now we are going to define a set of three new vectors. We'll call it A vector prime, vector B prime, and vector C prime. Now these three vectors are reciprocal system of vectors to A, B, and C if a vector A prime is given by the cross product between vector B and C divided by the scalar triple product of the vector A, B, and C. For vector B prime, we define it as the cross product between vector C and A divided by the scalar triple product between the vector A, B, and C. And for the third vector, vector C prime, that will be equals to A vector cross B vector divided by A, B, and C. Now, there are a couple of things that we can pick out from this particular idea. The first one would be, if we take the dot product between the vector A with its reciprocal, that is A vector prime, then this will be equals to 1. It also follows that this will be true for vector B dotted with vector B prime and vector C dotted with vector C prime. Let's try to prove this particular idea. So we'll begin with vector A dotted to vector A prime. So this means we have vector A dotted with, so we'll use the definition of our reciprocal vector A prime. So this will be vector B crossed with vector C divided by A, B, and C. So in the numerator, we have vector A dotted to vector B cross C, which is divided by vector A, B, C. Now here, by definition, A vector dotted to B cross C, this is the scalar triple product between the vector A, B, and C. So we have the scalar triple product of vector A, B, and C divided by the scalar triple product of vector A, B, and C. That means this, since both the numerator and denominator comprises of a scalar number, so that means they cancel out to give us 1. We can prove this for vector B dotted with B prime as well, and for vector C dotted with C prime. Point number 2. So if we have the vector A dotted with a vector from another system, that means we have dot product between vector A and B prime, or let's say we take the vector A and dot it with vector C prime, or similarly vector B dotted with vector A prime, or vector B dotted to vector C prime, or vector C dotted to vector A prime and vector C dotted to vector B prime. In all these cases, the dot product will be 0. So let's try out any one of them. Let's try out the last one. That means vector C dotted with vector B prime. So we have C vector dotted to the B vector prime. So that is given by vector C cross vector A divided by the scalar triple product between the vector A, B, and C. That means we have vector C dotted to vector C cross A divided by the scalar triple product between the vector A, B, and C. This will be equals to, now this is by definition is the scalar triple product of the vectors C, C, and A divided by the scalar triple product of the vector A, B, and C. Now if we consider the numerator, since we have two vectors that are exactly equals, which is the vector C, so that means the scalar triple product of this vector is going to be equals to 0. So we have 0 value. So this is what we wanted to show, that the scalar product of any other pair of vectors, one from each system, is going to be 0. Let's go to point number 3. So we have already discussed that the vector A prime, B prime and C prime, these are 3 non-coplanar vectors and are reciprocal to the vector A, B and C. Then in that case we can say that the scalar triple product of vector A prime, B prime and C prime, this is also going to be the reciprocal of the vectors of the scalar triple product formed by these 3 non-coplanar vectors. In another sense, we can say this will be equals to 1 divided by the scalar triple product between the vectors A, B and C. Let's prove that this is indeed true. So we'll start from the left hand side. So we have the scalar triple product between the vectors A prime, B prime and C prime. When we use the definition to expand it, we have vector A dotted with vector B cross vector C. Right. Then we'll have to use the definition of vector B prime and vector C prime. We'll use for A prime a little bit later. So we have A prime dotted with, so the definition of B prime will be C cross A divided by the scalar triple product between the vector A, B, C. This is crossed with C prime. So C prime will be vector A crossed with vector B divided by vector A, B, C. This is the scalar triple product. So we have, so what we now have is the the vector product of 4 vectors C cross A crossed with A cross B. So we'll have to use the definition. So here there's a particular way to expand this vector cross product of 4 vectors. So we'll begin with the third vector. So we have the vector A. So this will be multiplied to the scalar triple product of the remaining vectors. And to note down the remaining vectors, the scalar triple product will start with the next vector. So this is B vector. Then we'll come back to the beginning and again read from left to right. So we are left with vector C followed by vector A minus, then we'll consider the fourth vector reading from left to right. So we have vector B and this will be multiplied to the scalar triple product between the remaining vectors. So after B, we'll come back to the beginning. So we have vector C followed by vector A followed by vector A. Whole thing divided by vector A, the scalar triple product of the vector A, B and C square. By definition, this scalar triple product between the vector C, A and A, this will go to 0 because we have 2 vectors that are exactly equal. So we are only left with one term. So that means we have A vector prime. This will be dotted to this particular vector. There's a reason for that because this is just a scalar number. We cannot take the dot product of a scalar number with a vector. So the only way we can do that is take the dot product of 2 vectors. So here we are taking the dot product between A prime and A. So this is multiplied to vector BCA. So BCA, so this is cyclical in nature. So we can also write it as A, B and C and it would mean the same thing. Divided by A, B, C squared. So this is a scalar number. This cancels out with one of the scalar value in the denominator. And A prime dot A, we have already talked about it. This value is 1. So we are left with 1 divided by the scalar triple product of the vector A, B and C. So we started out with the scalar triple product of the vector A prime, B prime and C prime. So this is equals to the reciprocal of the scalar triple product of the vector A, B and C. Right. Now we have already mentioned that the vector A, B and C are non-coplanar, meaning that the scalar triple product of the vector A, B and C, that's a non-zero quantity. If this is a non-zero quantity, then it follows that the scalar triple product of the reciprocal set the reciprocal vectors a prime, b prime and c prime, that is also not equals to 0. That means the three reciprocal vectors are also non-coplanar. One is more evident, that if a prime, b prime, c prime, these are the reciprocal vector set to our vector a, b and c, then a, b, c will be the reciprocal vector set to a prime, b prime and c prime as well. Also, if we look at this particular concept, we can say that the scalar triple product between the vector a, b and c multiplied to the scalar triple product between the vector a prime, b prime and c prime, that's equals to 1. So this would mean that both of them has to be a positive or both of them has to be negative at the same time. In other words, what we are trying to say here, that if ABC is a right-handed system, then a prime, b prime, c prime must also be a right-handed system. And if one is a left-handed, the other automatically becomes a left-handed system. And finally, from all this result, we can say that our orthonormal vector triads, which is defined by I cap, j cap and k cap, the corresponding reciprocals will be I cap prime, j cap prime and k cap prime. That means we can say that I cap prime, this will be defined as j cap cross k cap divided by the scalar triple product between the vectors I cap, j cap and k cap. But the scalar triple product of I cap, j cap and k cap, that's always equals to 1. We can check that out. So by definition, I cap, j cap, k cap, the scalar triple product will be defined as I cap dotted to the cross product between vector j and k. Vector j dot crossed with k, this gives us the vector I cap, and the dot product between the unit vector I with itself is equals to 1. So we have j cap cross k cap divided by 1, and j cap cross k cap is I cap. So that means the reciprocal vector set. So we can say that I cap prime will be equals to I cap. Similarly, j cap prime will be equals to j cap, and k cap prime will be equals to k cap. Right. So now that we have understood the idea of the reciprocal set of vectors, let's work on few numerical problems. Problem number 1. We have three vectors. Let's name them as a, b and c. So we have vector a, which is given by 2i cap plus 3j cap minus k cap. We have vector b given by I cap minus j cap minus 2k cap. And we have vector c given by negative I cap plus 2j cap plus 2k cap. We have to find a set of vectors that is reciprocal to the given set. That means we need to find out vector a prime, b prime and c prime. So we'll use the relation to obtain the value of a prime, b prime and c prime. So let us begin by first obtaining the value of the scalar triple product between the vector a, b and c. So to find out the scalar triple product, all we have to do is obtain the 3 by 3 determinant, where in the first row we'll have components of vector a, so that will be 2, 3, negative 1. In the second row we have components of b, so that will be 1, negative 2. And in the third row we have components of vector c, so that will be negative 1, 2 and 2. Expanding along row number 1, so we have 2 times, so negative 1 times 2, so that will be negative 2, minus 2 times negative 2, so that's negative 4, but we'll have positive 4, minus 3 times, so we have 1 times 2, so that will be 2, minus negative 2 times negative 1, so that is 2, minus 1 multiplied to 1 times 2, so that's 2, minus 1, so this will be equals to 2 times 2, minus 3 times 0, minus 1 times 1, so we have 2 times 2, so that's 4, 4 minus 1, which is equals to 3. In the next step, we'll find out the cross product between vector B and C, cross product between vector C and A, and cross product between vector A and B. So let's begin. So we have vector A, B, and C. Let's determine the cross product between vector B and C. So this will be given by a 2 by 2 determinant. In the first row, we have the unit vectors I cap, j cap, k cap. In the second row, we have the components of vector B. So that will be 1, -1, -2. And in the third row, we have components of vector C. So that will be -1, 2, 2. So let's expand it. Along the first row, we have I cap multiplied to -1 times 2. So that's -2. Then we have +4 minus j cap times we have 2 minus 2 plus k cap. So k cap will be 2 minus 1. So solving this, we get 2 I cap. So this will be 0 minus 0 j cap plus k cap. So this is the value of vector B cross C. We'll then find out the value or the cross product between vector C and A. So we have I cap, j cap, k cap in the first row. In the second row, we have components of vector C. So that's -1, 2, 2. In the third row, we have components of vector A. So that's 2, 3, -1. So this will be, when we expand it along the first row, we should get -8 I cap plus 3 j cap minus 7 k cap. And similarly, when we find out the cross product between vector A and B, that was going to give us -7 I cap plus 3 j cap minus 5 k cap. So we have these three cross products. Now what we'll do, we will try to evaluate the value of each of the reciprocal vectors A prime, B prime, and C prime. So let's do that. So the reciprocal of vector A, which is A prime, so that will be equals to, we have E cross C. That's 2 I cap plus k cap. So this will be divided by 3. Then the reciprocal vector for B, which is B prime, so this will be equals to, so we have C cross A, so that's -8 I cap plus 3 j cap minus 7 k cap divided by 3. And finally, the reciprocal for vector C, that will be C prime, will be given by -7 I cap plus 3 j cap minus 5 k cap, all divided by 3. So these are the three reciprocal vectors of A, B, and C. Now let's go to the next problem. So we have problem number 2, which is quite similar to the previous problem. So let us begin. We will consider the vector A to be given by -I cap plus j cap plus k cap. The vector B to be represented with I cap minus j cap plus k cap. Vector C represented by I cap plus j cap plus k cap. We'll have to find out the reciprocals of each of the given vectors. That means we have to find out A prime, B prime, and C prime. Fine. So let's begin by determining the scalar triple product of the vector A, B, and C. So that means we have, in the first row, this is a 3 by 3 determinant. In the first row, we have components of vector A, so that will be -1, 1, 1. Second row, we have components of vector B, so that will be 1, -1, +1. In the third row, we have components of vector C. And when we expand it along the first row, this is going to give us a value 4. Right. Now, I'll note down the value. You can check them out. So we will also need to find out the value of B cross C, C cross A, and A cross B. So this will be equals to, so B cross C, so this will be -2 I cap plus 2 k cap. The value of C cross A, that will be -2 j cap plus 2 k cap. And the value of A cross B, so that will be +2 I cap plus 2 j cap. Well, that means our value of a reciprocal vector A prime, will be equals to, so by definition we have vector B cross with vector C divided by the scalar triple product of vector A, B and C. So that means this will be equals to vector C, negative 2 I cap plus 2 k cap divided by 4, or simply negative I cap plus k cap divided by 2. Let's find out the reciprocal vector B, the B vector prime. So that will be given by C cross A divided by the scalar triple product between A, B and C. So C cross A is negative 2 j cap plus 2 k cap. So we will have negative j cap plus k cap divided by 2. And C vector prime, this will be vector A crossed with vector B divided by the scalar triple product of vector A, B and C. So that means we will get I cap plus j cap divided by 2. So these three are the reciprocal vectors of A, B and C respectively. Let's go to the next problem. Problem number 3. We have three vectors A prime, B prime, C prime. These are the reciprocal system of vectors for three non-coplanar vectors A, B and C. Now what we have to do? We have to prove that any vector, any position vector R can be expressed in this particular format. So let's begin. What we'll do here, we will write our vector R as a linear combination of these three vectors A, B and C, such that we have x times A vector plus y times v vector and z times c vector, where x, y and z are some scalars. Let's call it equation number 1. Now what we'll do, we'll take equation number 1 and take the dot product with the vector b cross c on each side. So we have r vector dotted with b cross c. Similarly, we will dot each of the terms on the right hand side with b cross c. That means we have x for the first time, x multiplied to a vector dotted to b cross c, plus y times b vector dotted to b cross c, plus z multiplied to c vector dotted with b cross c. So we have x times, so this is the definition of the scalar triple product of the vector A, B and C, plus y times, so this will be the scalar triple product of vector B and vector C, plus z times, we'll use the definition, so this will become vector C, vector B and vector C. Now the scalar triple product of vector B, B and C, this will go to 0, and also scalar triple product of vector C, B and C will also go to 0. That's because we have two vectors that are exactly the same. That means we are only left with the first term, so that is x times vector A, the scalar triple product of vector A, B and C. So this is vector R dotted with B cross C. Since A, the scalar triple product is just a scalar number, we can divide both sides with the scalar triple product of A, B and C and solve for x. Then this was going to give us x is equals to R vector dotted with B cross C, whole thing divided by A, B, C, the scalar triple product. Now here if we look carefully, this is the reciprocal vector A prime. So that means what we have done, we have expressed dx as x is actually the x component of vector r along a direction, or the component of vector r along a vector direction, which is x. So this is given by vector r dotted with the reciprocal vector a. So let's call it equation number 2. If we use the same method, so that means next time what we'll do, we'll take vector r in equation number 1 and dot it with c cross a. So when we do c cross a, then this process is going to give us the value for y, which will be vector r dotted with b, the b prime, the reciprocal of vector b. So this will be equation number 3, and similarly we'll take equation number 1 take the dot product of vector R with A cross B, and this is going to give us the value for Z, which will be vector R dotted with the reciprocal for vector C. So this will be 4. So what we'll do, we will replace the value of X, Y, and Z obtained in 2, 3, and 4 in equation number 1. So this is our equation number 1. So that means we have R vector equals to X times A vector. So X here will be R vector dotted with the reciprocal of vector A. So this is X multiplied to A vector, plus we have Y. So Y will be R vector dotted to B prime. So this is multiplied to B vector, plus R vector dotted with C prime. So this is multiplied to C vector. So we have successfully represented the position vector R in terms of this given expression. Proved. Let's move on to the next problem. So in problem number 4, we have 3 vectors A, B, and C, which constitutes a set of 3 non-coplanar vectors such that the reciprocal vectors A prime, B prime, and C prime are given as followed. We have already talked about this. This is the definition. Here A prime, B prime, C prime gives the reciprocal system of vectors to A, B, and C. So what we have to show that the converse is also true. That means if we have the vector A, this is given by the cross product between vector B prime and C prime divided by the scalar triple product of the reciprocal vectors of A, B, and C. So let's do that. So we'll begin with B prime crossed with vector C prime. Let's begin with this. So here we will use the definition of B prime and C prime. So that means we have vector C crossed with vector A divided by the scalar triple product between the vector A, B, and C. And we're going to cross it with the vector C prime, and C prime is defined as A vector crossed with B vector divided by the scalar triple product of vector A, B, and C. Fine. So that means in the numerator, we have the vector product of 4 vectors, which is C cross A crossed with A cross B. And in the denominator, we have just 2 scalar numbers, that is the scalar triple product of A, B, and C squared. Now the task will be to find out the value of the vector product of 4 vectors. So here we are going to use the expansion. So first what we'll do, we will begin with the third vector as we read from left to right. So that means we have vector A. This will be multiplied to the scalar triple product of the remaining vectors. So right next to vector A, we have vector B. Then we come back to the beginning and again read from left to right. So we are left with vector C followed by vector A. Minus, now we will consider the fourth vector as we read from left to right. So this will be vector B will be multiplied to the scalar triple product of the remaining vector. So since we are at V, the vector next to B, for that we'll have to come back to the beginning. So we are left with vector C followed by A and then followed by A divided by the scalar triple product of vector A, B, and C squared. Now the scalar triple product of vector C, A, and A, this will go to 0 because 2 of the entries, the 2 vectors A, are exactly the same. So that means in the numerator, we are left with vector A times BCA, but BCA is equivalent to ABC. That is because the scalar triple product is a cyclical in nature. Divided. That means what I mean to say here, if we consider vector A, vector B, vector C, A goes to B, B goes to C, and C comes back to A. So we have initially the vector B. So we start at B, it goes to C and comes back to A. This is the same as saying we start out from vector A, go to B, and then reach out to C. So that means why we can write BCA, the scalar triple product, as equals to ABC. And also in the denominator, we have ABC squared, the scalar triple product of vector A, B, and C. So we can cancel out one term from the numerator and the denominator. So this leaves us with vector A divided by A, B, and C. So this is the value for the cross product between vector B prime and C prime. So let's cross multiply. So cross multiplying will give us vector A. This will be equals to B prime crossed with C prime. So this is multiplied to vector A vector B and vector C. And we have already proved that the scalar triple product of A, B and C, this is the reciprocal of this scalar triple product of A prime, B prime and C prime. We have already defined this, so that means we are going to replace this value with B cross C divided by A prime, B prime, C prime, and T gets scalar triple product. So this is the expression for our vector A. Similarly, using the same logic, we can also show that for vector B, this will be given by C prime cross A prime divided by the scalar triple product of the vector A prime, B prime and C prime. And for vector C, we will have A vector prime cross B vector prime divided by A prime, B prime and C prime. So we have successfully proved the following problem. Let's move on to the final problem. So here we have the three vectors A, B and C with the reciprocal vectors given by A prime, B prime and C prime. So we have to prove the following three. So let's begin with the first one. So we'll start from the left hand side. We have vector A crossed with its reciprocal vector A prime plus vector B crossed with its reciprocal vector B prime plus vector C crossed with its reciprocal vector C prime. That will be equals to A vector. We will be crossing with A prime. So by definition, A prime is given by B cross C divided by the scalar triple product of A, B and C plus vector B crossed with vector B prime. So B prime will be given by vector C crossed with vector A divided by vector A, vector B, vector C plus C vector. This will be crossed with C prime. So C prime is defined as vector A crossed with vector B divided by vector A, vector B and vector C. So let's combine them. So this will give us, so we have our big denominator. So we have vector A, the scalar triple product between vector A, B and C, and in the numerator we have A vector crossed with B cross C plus B vector crossed with C cross A plus C vector crossed with A cross B. Our next task will be to expand each of the vector triple product. So let us begin. All we have to do is remember the mnemonic. So when we have a vector A and this is crossed with B cross C, then their expansion is given by the mnemonic back cap, where B vector is simply multiplied to the dot product between vector A and C, and we have vector C multiplied to the dot product between vector A and B. So we'll use this to expand each of the three vector triple products. So for the first one we have vector B. This will be multiplied to A dot C minus C multiplied to A dot B. For the second term in the numerator, the second vector triple product, we have C vector multiplied to B dot A minus A vector multiplied to B dot DC. All you have to do is remember the position for back cap, then this becomes fairly easy. Plus we have C vector cross A cross B, so we have A vector multiplied to C dotted with B minus B vector multiplied to C dotted with vector A, whole divided by the scalar triple product of A, B and C. Now if we consider the first term, we have B vector multiplied to A dot C, and we also have look at the third term, we have negative B multiplied to C dot A. So this will cancel out. The second term, negative C vector multiplied to A dot B, so second term and the third term cancels out, and we have the fourth term and the fifth terms cancel out. That means in the numerator we only have 0. So that means this entire fraction goes to 0. So we have successfully proved that if we take the vector A, cross it with its reciprocal, plus take the vector B, cross it with its reciprocal, plus take the vector C, cross it with its reciprocal, then the sum of them will be equals to 0. Let's go to the second part. Let's begin with the second part. So we'll start from the left hand side. So in the left hand side we have vector A prime crossed with vector B prime. This is added to vector B prime crossed with vector C prime, plus vector C prime crossed with vector A prime. So vector A prime, this is given by vector B crossed with vector C divided by A, B, C, the scalar triple product. This is crossed with vector B prime. So B prime is given by vector C cross vector A divided by A, B, C, plus vector B prime. So our B prime is C cross A divided by A, B, C. This is crossed with vector C prime. So C prime is vector A cross vector B divided by A, B, C, plus C prime. So C prime will be vector A crossed with vector B divided by vector A, vector B, vector C. This is crossed with vector A prime. So A prime is vector B crossed with vector C divided by A, B, and C. This will be equals to, so that means in the numerator we have B crossed with C. This is crossed with C cross A divided by the scalar triple product of A, B, and C squared. So let's write the remaining two terms as well. So we have the vector product of 4 vectors. That means we have a vector quadruple product in each of the 3 numerators. So that means we'll have to expand it. So for the first one we'll start with vector C. So C vector will be multiplied to the scalar triple product of the remaining vectors. So that will be vector A, vector B, vector C, minus, so we start with the fourth vector. So we have vector A, this is multiplied to the scalar triple product of the remaining vectors. So that will be B, C, C, divided by A, B, C squared. Similarly, let's compute the vector quadruple product for the numerator. So we'll have A vector multiplied to the scalar triple product of vector B, C, A, minus B vector multiplied to vector C, A, A, whole divided by A, B, C squared, plus the third term. So in the third term we have vector B multiplied to the scalar triple product of C, A, B, minus C vector multiplied to A, B, B, whole thing divided by A, B, C squared. Now, if we use the definition of a scalar triple product, so this term will go to 0 because we have C vector and C vector repeating. Here, this will also go to 0. A vector is repeating, and we have B vector repeating. So this scalar triple product goes to 0. Now what we'll do, we'll combine all the 3 terms to get, from the first term we have C vector multiplied to A, B, C, plus from the second term we have A vector multiplied to BCA. BCA is actually the same as A, B, C, plus the third vector, which is B vector multiplied to CAB. So CAB also the same as A, B, C, whole thing divided by the common denominator from each of the 3 terms, which is A, the scalar triple product of A, B, and C squared. Now we can take the scalar triple product A, B, and C common from both the numerator and the denominator and rearrange the terms to leave us with vector A plus vector B plus vector c all divided by vector, the scalar triple product of vector a, b, and c. And this is the right hand side. This was what we were asked to prove. Let's do the third and the final part. The third part is very simple. We have already talked about that of when you take a vector a and dot it with its reciprocal, then its value is always equals to 1. Same goes for the vector b dotted with its reciprocal, that's also equals to 1. And vector c dotted to its reciprocal gives us 1. When we add the three terms, then we have vector a dotted with a prime plus vector b dotted with vector b prime plus vector c dotted to vector c prime. So this will be equals to 3. Right. So this was all about reciprocal vectors.